Yeah, so since I was not recording, I'll just repeat what I had told already. Uh, can anyone confirm, Nikhil, did I teach you this one, the magnetic dipole moment of a revolving electron? Did I teach this part? In the last class? I don't remember actually. Can you confirm in the message box, chat box? Did I teach you this magnetic dipole moment of a revolving electron? Can anyone tell me? Maybe I don't know who was there in the last class. Nikhil was there, and Pujita was there. I think. Okay, let me check here. Okay, Nikhil, are you people able to hear me? I hope you people are listening me. Can anyone confirm that whether this part was covered in the last class? Okay. Anyway, so this is independent of our discussion today. What I have started already, the moving coil galvanometer. Okay, if time permits today, I'll discuss once again this magnetic dipole moment of a revolving electron after I finish this galvanometer part. Okay, let me start with the galvanometer part itself. So today, first let us discuss moving coil galvanometer. Okay, so before I start directly moving coil galvanometer, I'd like to just make you recap few things which I had already taught in the last class. So this is, see, if we keep a current carrying low in a uniform magnetic field, it will experience a torque which can be expressed by cross product of this M cross B. This is M is the magnetic dipole moment, and B is actually the magnetic field. And how do we write magnetic moment? The magnitude of the magnetic moment you will get by multiplying the total current with the area. This is a vector quantity. Since area is a vector quantity, area will take the direction of the area is always outward normal to the plane of the loop. So that is the direction of magnetic moment. So you can even use the right hand thumb rule also. If suppose this is a plane like square loop, and you have a current which is flowing in the anticlockwise direction. If this loop is on the horizontal plane, then you can use your grip rule, right hand grip rule, to find out the direction of the magnetic moment. Okay, this will be upward, in the upward direction. If the current is in the opposite direction, clockwise direction, you can just look that the magnetic dipole moment will be in the downward direction if the current is in the opposite direction. Okay, so this is how we have learned that if we keep a loop of a current loop in a uniform magnetic field, it will experience a torque. So this particular fact will be used in moving coil galvanometer. As I said, moving coil galvanometer. So there is a coil. You look, this is the coil. See, there it has been shown only one coil. Here you can see a number of coils, like many number of coils are there, and these coils are kept inside a uniform magnetic field. You can see these are called cylindrical electromagnets, cylindrical shape, cylindrical electromagnets, cylindrical shaped electromagnet. What does electromagnet do? Electromagnet, while you pass the current through electromagnet, it will create a magnetic field. And why do we take this as cylindrical shape? You look, this part is cylindrical, right? This cylindrical shaped electromagnet. So it means actually this cylindrical electromagnet will create a radial magnetic field. Okay, a radial magnetic. So what is the galvanometer? It is nothing but a loop of wire, not a loop. There are many turns in the loop. So a loop of a current loop which has many number of turns. You can see these are the wires, and so you can see small arrows also there. Arrows are there depicting the direction of the current in this. Okay. This particular figure is taken from website. Particular website I have. So internet. So you can even see in your uh, computer when you read this part, and this figure will give you the clear view of what is called galvanometer. So you have this at the electromagnet. You can see the north pole and south pole, and this is cylindrical shape which creates a radial magnetic field. And you can see this is a loop, the deep brown color current carrying loop, and there suppose there are n number of turns, and each is carrying current I. So there are n I current is flowing through that. Okay, and look, this is another one. This is actually a soft iron soft iron core. Soft iron core. So why do we use this soft iron core? This core is placed inside the loop. See, earlier I have shown you this loop. So nothing was there inside this. Okay, nothing was there inside this. But now what we have done, we have taken a core, and this core is also of cylindrical shape. This is soft iron core. What does this do? This do what? Actually, this makes the magnetic field which are created by this electromagnet further uh, uniform. Further radial. That means it will make perpendicular to this cylindrical. So I'll tell you one thing. So look, if you have a cylindrical symmetry, always electric or magnetic, whatever you say, the magnetic or electric field, whatever it is, this field will be always coming how radially outward. So you can see in this case, this is making a perfectly 90-degree angle. If you keep this cylindrical, this soft iron core, it is making the magnetic field. This is the magnetic field, and this is the aim. Aim is along the direction of the area vector of the loop. See, this is the loop. That means your area vector is exactly downwards. Okay, downwards like this. So it is making a 90-degree angle between them. So earlier we have seen that we have got torque is mb sine theta. Okay, sine theta. This is the angle between M and B. If it is 90-degree, then the torque will be maximum in this case. The torque will be maximum. Okay, if theta is 90-degree. So to do that, this kind of cylindrical shape, soft iron core has been used in this galvanometer. Okay, so that part is done. So cylindrical shape electromagnet, cylindrical shape iron core, and one more role is there for this cylindrical shape soft iron core. Any iron core, whenever you keep in a current carrying loop, inside a current carrying loop, it will increase the strength. What it will do? Increase the strength of the magnetic field. Increase the strength of magnetic field. Okay, what it does? Increase the strength of the magnetic field. Increase the strength of the magnetic field. Okay. Of B. So these are two roles. One, to make the magnetic field radial, okay, like this, and to increase the strength of the magnetic field of the galvanometer. All right. So now look here. See, there are two springs. One, see, there are two ends of the loop. Okay, there are two ends of the loop. You can see that this is one end of the loop. Another one is this one. So these are two ends of the loop of this wire. Okay, or coil, I should say. There are two ends of the coil. Okay, so these two ends are actually connected by two springs. This is in your book. It is written as SP. There are two springs which are connected to this screw, and another screw is this one, which is connected to this side. You can look this, and through the spring itself, you can send the current, or you can do the biasing, electrical biasing with the battery and all. Okay, or you can connect. These are actually leads of the. These are leads of this positive and negative which you see here. This is the leads of the galvanometer. Leads of the galvanometer which you connect with the circuit. Galvanometer. Okay. And see, there are two springs, as I said. These springs are actually connected in the opposite way. And you know, like when this loop try to rotate because of the torque experienced by the loop, which is actually obtained by this one MB, or in vector term it is M cross B. This is actually due to the uniform magnetic field. Due to the uniform magnetic field, this loop will, or this coil will feel this torque, and you know, like torque will try to rotate. Torque will try to rotate the loop, this coil. Okay, rotate the coil. See, the direction of the rotation has been shown like this. Okay, this clockwise direction in this case. Okay, if the current direction is this way, magnetic field. Okay, magnetic field will be again. So you can understand that the torque experienced by this coil is making the coil to rotate, and in such case, when the coil will try to rotate, look, these springs are there which will be actually compressed, right? That means when they compress, they are becoming compressed. You know, like in your 11th standard, you might have learned when a spring is compressed, so it will give a, if it is compressed, so it will give a force minus kx kind of that. Okay, so anyway, it will give a force. So there will be a force in this. See, there will be two opposite forces on this loop there. So this is one spring, another spring is this one. So there will be two anti-parallel springs. If this is force this way, this force will be this way. Okay, and these two forces also will create a torque on this loop. This torque, which is given by the springs attached to the ends of this coil, will counteract the torque which is created by magnetic field. So the whole thing is this magnetic torque will be created by the torque given by, so torque given by this spring. Okay, so this is the whole matter over here. Okay, this is magnetic torque will be counteracted. Okay, counteracted by this torque which is appearing due to the springs. Okay, so this torque will try to bring the coil in its original position. So at equilibrium condition, this magnetic torque will be exactly equal to the torque given by the spring. We will see all the mathematical details. Okay, so this is the construction of the, and you look here, that's since these two are actually counteracting to each other, so whenever due to the magnetic torque the coil is rotating in certain direction, the torque due to the spring will counteract that particular torque, magnetic torque, to counteract to counteract the magnetic torque. So because of that, you know, this, see, there is a needle over here, you can see this, or pointer. This pointer will actually pointer is also connected to one of the spring or one of the side of the loop itself. Okay, so this pointer will be actually deflected. Deflection means what? Deflection means, suppose it was here, it will just go to somewhere and then immediately come back to zero again. If this is the neutral condition, then there was, so okay, so all these things will happen when there is a current through the coil. Okay. So now I'll just tell you what is the role of this galvanometer. So galvanometer actually can be used as ammeter. Ammeter, you know what is the role of ammeter? Okay, to measure the current. Okay, to measure the current, to measure current in the circuit, and it can be used as voltmeter as well. So what is the use of voltmeter? To measure the voltage across any part of the circuit. Okay, across any part of circuit. Okay, these are two main roles it has, and you have been say reading the galvanometer like given in a question quiz. Do you remember that? And there, if there is no deflection, there is no current through it. So that means, you know, like it can tell you whether there is a current in the circuit or not, and it can also quantitatively help you to, it will help you to quantitatively measure how much how much ampere is flowing through a circuit. Okay, and some galvanometers are there which will tell you the flow of charges also. Okay, that is actually ballistic galvanometer. Here actually we see that the galvanometer can be used to know the presence of current or to measure the amount of the current in the circuit, as well as to measure the voltage across any part of the circuit. Okay, so this is the role. And by seeing the deflection, you look here, this is a scale actually. This is scale. This scale has been made by calibration. Like see how much magnetic torque is appearing due to the given coil. If the magnetic field is known, okay, if the magnetic field is known, and how much, you know, the spring, if you know the spring constant, etc. So from there also you know what is the torque given by this spring itself. Okay, so knowing that, you can see, you can know the amount of the angular deflection. You look, angular deflection means, suppose this is a neutral point 0. Okay, so from here you can draw this line. You can see this is called phi. Okay, this is called phi. This is angular deflection, and that angular deflection will give you the amount of the amount of the current, which you can see from the scale graduation. Okay, so this deflection is actually calibrated with this scale, having the numbers of like 1 ampere, 2 ampere, 3 ampere, 5 ampere, etc. Okay, so yeah, so this is how it helps us to, and this is the concept, and this is the working principle of this moving coil galvanometer. So this figure is not from your book. I'll just show you. So this is actually the whole picture of the galvanometer originally. Now you look the figure given in your book. Okay, given in your book. So these are, it is so actually in the device format. These are actually permanent magnet in the device. These are permanent magnet. So north and south pole cylindrical shape, as I said in the earlier presentation or earlier slide. This is the coil. Okay, and see the spring is connected to the coil. Okay, there are two springs as well there, and this part is actually here kept empty, but there I had shown you that these are connected to the screw, some screw. Okay, and this is the pointer which will tell you how much current is flowing through the circuit. Okay, or how much voltage. If it is a voltmeter, if you are using this as a voltmeter, you'll get the reading from here. So this scale has been actually made by calibration. Actually, calibration. How do you calibrate? How much angular deflection is how much? So how much angular deflection, if I say phi, is equivalent to how much ampere current. Okay, so this relationship has been developed, and then the scale has been made. Okay, this is this will give you direct reading of the voltage of the current. So this part, you know, this view is actually a top view of the galvanometer. Okay, top view. This one is top view. That's why it looks like this. You don't see the whole cylindrical shape, this core. You don't see the whole one. You don't see the other end of the coil also. This is the top view, top to bottom. Okay. So that's why it looks like this. And you look, these are the magnetic field, radial magnetic field, and it will be actually exactly magnetic perpendicular to the magnetic dipole moment. Okay. So that's why this cylindrical shape, this core has been used. Anyway, I have told the construction. You can read now and then see what it is there in your book. Now, I told you the uses also, and I have told you what. See, this coil has actually many numbers of turns. Suppose I have a number of turns, and when there is a current I in each coil, okay, each coil, and if each coil has area A, then this is the magnitude of the magnetic dipole moment. Okay, and as I said, these are two perpendicular according to our construction. So the angle between them is actually 90 degree. 90 degree. Now I know when I keep a coil to which a current is flowing I, and that coil is kept in a uniform magnetic field. So I write when a coil is kept in a uniform magnetic field. I hope you know the term uniform. Uniform means magnetic field is constant everywhere in the region. Uniform magnetic field, and some current is flowing through the wire of the loop through the loop. Okay, some current suppose here I, then the magnetic torque experienced by the loop will be mb. Okay, this is m cross the tau b, m cross b, and I just said this is 90 degree angle, so mb sine 90 degree is 1, so I am writing m. So this is the magnetic torque the coil which we are discussing over here will experience. If this is the torque, magnetic torque, this magnetic torque, as I said, this will be counteracted by your torque given by the spring. Sorry, is spring. Okay, that torque, magnetic torque, will be counteracted by the torque produced by spring. So the spring will produce a torque which is actually which will be exactly equal at the equilibrium situation. At equilibrium. Okay? At equilibrium. So from here we will find out the relation between current, voltage, etc. Let us see. So I can write the spring torque is as k into phi. So this is the angular deflection which is directly related to your deflection of the pointer in your device. Okay. This k is actually torsional constant. This is called torsional constant. You might have learned what is torsion called. And this is N I A. This is M and this is B. So this is the torque. So this is the equation I have got for galvanometer. So from here I can find, so this K is actually torsional constant. Torsional constant. It has unit, this is deflection part. Sorry, this is actually the deflection. If you write this K, K is per unit deflection. Okay, the torque per unit deflection, that is called actually K. That is the unit of K. So this is the torque per unit deflection. It's called torsional constant. Okay. So you look here, how much deflection you will get. That you will be able to get from these parameters. Okay. So this particular torque, this is constant for any galvanometer. Look, this K is constant because the material of the spring is always fixed. N is the number of turns in the coil. A is the area of the coil. B is the uniform magnetic field. So this torque is always a constant for a given galvanometer. Okay. Now look, you can see that this phi is then directly proportional to R. That means you can, if you know the relation between this is, they are actually directly proportional. If the current in the circuit is more, deflection is more. If the current in the circuit is less, then deflection is less. Okay, so this is how you can get. Okay, now I just tell you that the galvanometer can be used as ammeter. We'll see first the galvanometer as an ammeter. So galvanometer as it is cannot be used as an ammeter. There will have to do some modification. Okay, some modifications are needed. So what are the modifications? Let us take one circuit and I will just use the galvanometer as an ammeter. How do we do that? So suppose I have a battery. You have learned the electricity part in the third chapter. So I'll just draw an arbitrary circuit. Okay, and I have to. So this is some battery. This is battery. Current is flowing in this way. So I have to measure the current in this circuit. Suppose this as R1, this is R2, some load resistance, and this is actually a bulb. Okay, I have to find out what is the current in this circuit by using galvanometer. Let me tell you, galvanometer has actually a high resistance, which I will be writing as RG. So galvanometer has high resistance. High resistance, okay? Galvanometer has high resistance. So suppose I want to calculate or measure current in this circuit, I have to use ammeter. You might have already learned that I have to use the ammeter in a series, okay? In a series. So I just let me use this ammeter here as this. Suppose this is an ammeter. If I use directly the galvanometer, what will happen? It has huge resistance. This galvanometer coil has a huge resistance. So what would have happened? See, if you use in the series a high resistance, the whole current, okay, whole current will change in the circuit, right? It will resist the current itself. So whole current, suppose earlier it was 12 ampere somehow. Now see, after using this ammeter, like galvanometer as an ammeter in a series, it would actually resist the current. Maybe you will get some micrometer or milliampere or something. Maybe some 5 milliampere you are getting current. Now in the circuit, the whole current will be affected in this case. So to avoid this thing, like whenever we use any measuring instrument, the error it produced in the measurement has to be less than 1% by this measuring instrument. Okay, less than 1%. So if we measure anything in the circuit, due to this measuring instrument, the error which is happening in this circuit or in the measurement has to be less than 1%. So this is the kind of accuracy we need in our like application purpose. So that means the current has should not be disturbed by this measuring instrument. So what should we do? So to avoid this thing, what happens in the galvanometer? Suppose the galvanometer I have, in the galvanometer I have, this is galvanometer G, and it has a very large resistance. Okay, so what I can do, I can use a very small resistance. This is called shunt. Okay, this is called shunt. Very small resistance in parallel to this galvanometer. Like if it is in parallel, then what will happen? If suppose this Rg is much greater than R, see this, I'll say the resistance is Rs here for the shunt resistance. And this is the galvanometer which has very high resistance. And along with, see, to avoid this problem which I have discussed in the circuit, I'm just connecting a very small resistance in parallel to this galvanometer. So what will happen in this case then? See, I'll write, like you have learned what is the equivalent resistance for. So I'll write equivalent resistance for this circuit, this circuit. So I know it will be Rg into Rs divided by Rg plus X. Okay. Now, if Rg is much greater than Rs, so what this equivalent resistance will be? Look, this Rg is much greater than Rs, so I can cancel this one. So you can cancel this one and this one. You will get equivalent resistance of this galvanometer. This whole combination of this shunt and this galvanometer is Rs. So this Rs is actually some milli ohm or some ohm. Suppose 1 ohm, 10 ohm, okay, or maybe some milli ohm also. Very small resistance. And whenever we use a very small resistance in a parallel to any circuit, that is called shunt. It is called shunt. And in this case, look, if the current is coming as 12 ampere over here, so how much current will be? Is the current now too much affected by this circuit now? If this is suppose some 1 kilo ohm resistance and this is some 1 ohm resistance. So like after reaching to this point, this whole 12 ampere current will almost pass through this way. Then some microampere current will go in this way. Okay, some microampere current maybe will go to this current. Okay, the whole current, almost the whole current will pass to this shunt. Almost the whole current will pass to the shunt. So if you use this combination in this circuit now as an ammeter, no current is getting resisted by this or restricted by this ammeter now. Okay, so I just quickly tell you what we have done now then. So if I have a galvanometer, okay, this is the Rg. So if you want to use this galvanometer as an ammeter, so you have to use a very small resistance as shunt with this galvanometer. Then what will happen? The whole current, suppose there is some current I, so there will be I1 through this and I2 through this, and I2 is actually nearly equal to I. So this is what we have seen. So now this is connected in a series. So the whole current, almost the whole current will pass through this way. Okay. So this is how you can use the galvanometer as an ammeter. Okay. And look, the sensitivity of the ammeter can be found out. Look, I have got phi is equal to, from the previous equation, NIA B by K, if you remember that. Okay, or I can write this as NAB by K. This is a constant for a given galvanometer, and this is the phi. So sensitivity, this is called current sensitivity for an ammeter. Current sensitivity, that means how much small current it can detect. Okay, that is the sensitivity. This is limit. This is called limitations of the ammeter also. Okay, beyond this, like below this current, this much current, galvanometer or this ammeter cannot sense. That's why it is called current sensitivity. It is defined as, see if I write from here, phi by I, the deflection per unit. So deflection of the pointer. Okay, as I showed you in the previous, this is the deflection from, suppose this is the equilibrium position, this is the phi. Deflection of the pointer per unit current. Per unit current is defined as current sensitivity. Then current sensitivity is given by NAB by K. So if you want very high sensitivity, you look here, you keep all the things as it is. You can increase, just you increase this N number of turns in the galvanometer coil. Okay, so then you can easily increase the sensitivity of the current sensitivity of the ammeter. Okay, so this is called current sensitivity. I hope you have understood. This is NAB by K. This is actually current sensitivity. Okay, and current sensitivity can be double. So it can be double if your N is now. Say if your N is 2N, then what will happen? So suppose this is so yeah. So new current sensitivity will be new current sensitivity. Suppose phi. This is prime, and look here. What will happen if this is 2NAB by K? Because other things will not change. So let's see, this is 2 into phi by I. So the previous one. Okay, this is this one. Okay. So you can double, triple. You can just get this multiplicative factor with the number of turns, and you can increase the sensitivity, current sensitivity of the ammeter. And there are many interesting numerical problems related to this. I'll be actually sending you some problems regarding this chapter. Okay, on this chapter, and then next class we will discuss many problems. Okay, numerical problems. So now we'll just go and see that galvanometer as a voltmeter. That means how can we use galvanometer as a voltmeter? So what does voltmeter do? Suppose I have a circuit over here. I have many resistors. I have one bulb over here. Okay, and anything maybe you can use again. So I am just closing the circuit over here. Okay. So suppose this is R1, this is R2, this is some voltage. Okay, in this circuit, suppose we want to calculate the voltage drop across this R1, suppose the R1, or maybe across this two, the R2, or across this bar. Okay, what we can use is voltmeter. The instrument, measuring instrument, is the voltmeter, and that device you have to connect actually in a parallel to that particular section where you want to know the voltage drop. Suppose I want to know the voltage drop over here. My voltmeter has to be connected like this. This is voltmeter. Okay. in the parallel connection. Okay, this is parallel connection. It's parallel to the circuit element. Okay, parallel. So now look, as I said, the galvanometer we cannot use here directly as voltmeter. We cannot directly use here the galvanometer and then connect it to parallel to the circuit. Why? Because I have told you that galvanometer has a huge galvanometer. It has huge resistance with it. If you connect, what will happen here? You know, the voltage will get, let's say, some minimum amount of current also goes to this. It will have a huge voltage drop across this itself, across the voltmeter itself. Okay, across the voltmeter itself, because it has very huge resistance, something like some kilo ohm to some 10 kilo ohms, like that. Okay, order of 10, like that. Okay, so it has a very huge resistance. So if suppose some small amount of current is flowing through this voltmeter, then it will actually drop on almost a huge amount of voltage from the battery, and it will make, like, it will, what it will do, it will disturb the other component. Okay, that means if your bulb was glowing, okay, earlier, after using this voltmeter you may not see this glowing. Okay, may glow may glow may go off because of sort of voltage across this. Okay, across this. So what? Because if you use this galvanometer directly like this, so if a small amount of current, suppose some micro ampere also goes to this galvanometer, it will draw a huge amount of voltage from the battery. So the bulb will not get the sufficient voltage to glow, okay, or power to grow. So this kind of problem may happen if you directly use the galvanometer. So you are intelligent, so what you might have understood what I'm trying to say, that what is the modification we should do with the galvanometer so that you can use the galvanometer as a voltmeter. So that is my question now. So what modification you should be doing to use the galvanometer as a voltmeter in the circuit? Look, I will be using that in the, see, suppose this is my resistance, I have to use the voltmeter like this in parallel. Okay, now look what happens. So if my galvanometer has actually some resistance, already some resistance is there, it is a large resistance obviously, but still, to ensure that no current, almost no current, or very less current is flowing through the galvanometer, to ensure that we will be using a resistor which is called RS in the series of this galvanometer. Okay, so look here, what will happen, you know, this is much here again, RS is much greater than your RG, much greater than R. So a huge resistance you have to connect in series with the galvanometer to use this as voltmeter. Okay, if you want to use this as a voltmeter. So look what will happen in this case if we use a very huge resistance in series. Okay, in series of the galvanometer. So I know the equivalent resistance will be RG plus RS. If your RS is much greater than RG, so I can write this equivalent resistance nearly equal to RS. That means, suppose this is 100 kilo ohm, this is maybe some 1 kilo ohm. So you can neglect this effect of this, and you can see this effect. Yeah. So as a whole, you know, you'll get very huge resistance internally. This is called internal resistance. Very huge internal resistance for a voltmeter. Very huge internal resistance. This is called very huge internal resistance. So this huge internal resistance will not allow any current, like all, no, some current has to be flowing through this, but very less current, which will not hamper the voltage across the other circuit element. Okay, if your current is very less, say the voltage drop across the voltmeter or measuring device there will not be much larger than your or not even larger than the voltage drop across the other circuit elements. Okay. All right. So I have got this idea that we have to use a huge resistance in series with the galvanometer, and that can be used as a voltmeter. All right, very nice. So in this case also I'll be writing the equation which we have learned for equilibrium case. So we look here, phi was N A B by K and then I, like that. So what is the voltage sensitivity? Voltage sensitivity also has been defined as deflection of the pointer per unit voltage. So I will just divide this part with voltage. Okay, right hand side also with voltage. So look, this is actually 1 by R. So NAB by K is actually 1 by R. Okay, this is 1 by R. So you can see this is the voltage sensitivity. But now can you tell me whether just by increasing the number of turns you can increase the sensitive voltage sensitivity or not? So the answer is actually just by increasing the number of turns, you will not be able to increase the voltage sensitivity. I'll tell you why. See, when I have seen that the current sensitivity can be increased by increasing the number of turns, I'll write these two sensitivities side by side. So this is current sensitivity, I by I. What I get here is this. Okay, and what is voltage sensitivity pi by V? What I get is NAB by K into 1 by R. So look, if I want to increase the current sensitivity by increasing the number of turns in the coil, whether the voltage sensitivity also will increase. That is my question. So question is, when I am increasing the number of turns, okay, this N, to increase the current sensitivity, Vt, that is pi by I, whether voltage sensitivity also increases or changes. Okay, is there any change? Voltage sensitivity increases or not? So this is a small question. If you look this thing, look, I'll just make my n prime now 2n. So earlier also I have told you, see my new current sensitivity, suppose 5 by I prime. Okay. So look, in the current sensitivity part, n you make 2n, so it will be 2 pi by I. This is the new one. Okay. So this will be double of the previous sensitivity. Now, if I increase the n over here to 2n, what will happen? Will this be also increasing by 2? The answer is no, because when your length of the wire in the loop or the coil, this is n is actually number of turns. That means when your number of turns tending to 2n, then your current in the wire also will increase. Okay, and it will be almost proportionally increasing. So R prime will be 2 1. So if you just put this 2, then you look 2 will get cancelled from numerator and denominator. and finally the voltage sensitivity remains the same. So that's why when current sensitivity increases, not necessarily voltage sensitivity will increase. Okay. So this is actually a whole part about this galvanometer. I'll show you here in the board. So what I have discussed here, the whole thing I will show you here, and I have, okay. So this is whole part over here. If people have to carefully read it, and in the next day, I'll take a few examples regarding this galvanometer, okay, and as well as other problems also. Probably I'll send you some of them in the WhatsApp who are there. They can circulate to others. Help. I think I can send to Guna Madam also, so that you can get from her. So I think I'll stop it here for today. Already 3 people are there. Others have left. So next class will be numerical problem on this particular chapter. Okay. Okay. So if you people have any quick question or quick doubt, who are here, Mridula, Pujita, and Chandana, if people have any doubt regarding today's topic or maybe any part of this chapter, you can ask me 2-3 minutes. Otherwise, I'll end the class. Pujita, Mridula, do you have any doubt, any question, any query for today's class? Anyway, I'll come to know in the next class, because I'll be sending few questions on this particular chapter. I'll send it to Guna Madam, who will circulate to you people. Maybe by tomorrow morning, I'll send the questions. Mridula, do you have any doubt, any questions? Pujita, do you have any doubt, any question? Okay, no. Mridula saying no. Okay. What about Pujita? Do you have any doubt? Yeah, this is something, some Deepa. Deepa,
No, sir.
I don't know whether you were there in the meeting. Yeah, do you have any doubt, any question, any clarification for today's topic,
No,
or maybe
sir.
any part of this chapter? No, okay. So yeah, so I'll send some questions to Guna Madam. She will circulate to you people to try to solve. Those questions will be mostly numerical problems, which will be of standard of your board exam as well as competitive exam. So those questions will be discussing in the next class. Okay, today is Sunday, so in the next class Wednesday we'll be discussing those numerical. So by this we actually end this chapter. If you people have any doubt, any question, or any query, you people can contact me through Bruno Madam, or by any means I'll clarify you, or maybe in the class also you can ask me. Okay, in the next class. Okay, then I'll stop it here. Okay. Yeah, bye.